I want to ask you again, what is parallax? So what is parallax? I think we talked about stereoscopic viewing, but did we talk about parallax? I don't think we did, right? Okay, so we are going to talk about parallax, stereoscopic parallax. But before we talk about stereoscopic parallax, let's talk about what parallax itself is. Parallax is what you experience when you are sitting in the car and then you look out the window. You see that the trees that are very fast seem to be moving very fast. That is parallax you experience. Parallax is what you experience when you go to Inzolenzo in the western region. And then when you actually are approaching the village, which is suspended on water, then you realize that it seems the buildings are moving. You know, and in fact, that the parallax you experience at Inzolenzo is extremely, in fact, it's fascinating. You know, it's like magical almost. You see the buildings like shifting as if one is moving behind the other. Wow. In fact, the day I saw it, but I knew what it was. So, and yet when we got down and I asked them,
so I've been there.
You experienced that parallax too? Did you experience it?
I don't really remember because it's been long.
Okay,
I don't remember.
But
I know about the trees.
Okay, the trees one day, I think anytime we sit in a car, we experience it. You know, so parallax is really the apparent movement of an object attributed to the movement of the observer, okay, against a certain frame. So there's always got to be some kind of reference frame from which the movement is done. Okay, so that is what we know to be parallax before we talk about stereoscopic parallax. So what is stereoscopic parallax? So then remember that we talked about stereoscopic viewing, which is really about looking at photographs with the left eye looking at the left photograph and the right eye looking at the right photograph. Okay, and then when we do that, then the parallactic angles are formed, and then we are able to now observe or experience depth, which is perceived depth, how deep something is, how far something is from us. Okay, so that is by way of refreshing ourselves. Okay, but then when you combine the parallax and the stereoscopic, viewing, so stereoscopic parallax, then it gets quite interesting. So stereoscopic parallax has something to do with the plane, the airplane moving from one point to the other. And by so doing, you having the object on the ground moving within a common reference frame, and the reference frame will become the photograph. So when you look on one single photograph, if you could superimpose the left photograph and the right photograph, you will realize that there is a movement of the object from one point to the other, or there's a change in the coordinates, okay, between, for one particular point or image point. Let me put it that way, image point. So for an object on the ground, it is seen twice. How is it seen twice? At the exposure station on the left-hand side, we see the object. And the exposure station 2 on the right-hand side, also, we see the object. So we've seen it twice. So it's like we are moving. But then what is happening is that the object that we are looking at seems to be moving, but it's not really moving. Okay, so it's important for us to recognize that the plane is always, the object, the platform. I shouldn't be saying plane. It can always be a drone. Okay. And then we have an observation like that. Okay, when it moves forwards, we can now talk about a new exposure station. So L1, L2. Okay. So the plane is now here at this point. Okay. Now what that happens, an object which is, let's say if there's a tree here, the tree is being captured within the first exposure, okay, and then in the second exposure, it's also being captured. And we now have a situation where on the photographs, there is a change in coordinates. Are you okay? So we have the same point appearing here, somewhere here. And then as we move forward, or let me bring it a bit closer to here. Let's put it here. It's okay, going to disappear if I do that. Then if we actually take the second photograph, we will realize that there is this change in location of that same point that is seems to be now moved backwards a bit. So now there is a change in the object's position. It's apparent because when you fly over an area, the things over there don't move along with you. Unless in some cartoon world, okay, unrealistic world. But in the real world, when you travel and the trees are moving, they are not really going anywhere. They are actually where they are in that, so this concept of the object, the point image on the object shifting is what we are calling stereoscopic parallax. Is okay, is the X parallax, and it's interesting to study. And that is why we are here today, to look at, what we can do with that parallax. Because see, the Y parallax is a bad thing. We don't want Y parallax. So this parallax I'm talking about here is actually the X parallax. So this is X parallax, and it's along the X-axis. It's measured along the X-axis, and it's natural. It happens naturally. You don't have to, like, once you are moving from one place to the other, what do you expect? Okay, excuse me for sounding a bit cheeky, but yes. But Y parallax, we don't want that. It's as a result of the non-alignment of the photographs, or maybe unequal flying height. We talked about all the various causes of the Y parallax, which is really an error. Are you okay? So let's look at what I have in your notes, this handout here. Parallax, apparent shift in the position of an object with respect to the frame. So I'm going over everything I've just said. With respect to the frame of reference caused by a shift in the position of the observation. I think this is just clear to everyone. Is that okay? Now, change in position of an image from one photo to the next is caused by the aircraft's motion. Okay, so the aircraft moving from one point to the other is what we're considering the aircraft and the camera mounted on it to be the observer. Are you okay? So it's as if you are in there. So that's what we're talking about over here. Changing the position of an image from one photo to the next is caused by the aircraft's motion and not by the object itself on the ground. And we want to call it the stereoscopic parallax, the X parallax, or simply parallax. Easy peasy. Okay, someone has a question. Go for it. Someone put up their hand, or they are not aware. Should I just move on? I didn't even check who it was. Okay, okay, it's by mistake. So let's move on. So that is what stereoscopic parallax is all about. The X parallax is okay, and that is what we want to look at. And then the Y, we are not interested in the Y parallax, which is an error. So two important aspects of stereoscopic parallax. Parallax of any point is directly related to the elevation of the point. Okay. The elevation of a point is related directly to the parallax. Okay. So the parallax of any point is directly related to the elevation of the point. We will know that too. The parallax is greater for high points than low points. So, I mean, it's easy to remember this. Parallax will be high for an object that is closer. So what does it mean in terms of the trees? Parallax is greater for high points. So a high point is an object which is closer to us, which means that when we are driving, the grass and the trees that are closer to the road, they seem to run faster than even the ones that are far behind. Anyways, that is what this is saying. So we can actually, double check that. In theory, this is the geometry. This is the geometry of parallax. Is that okay? So now let's study this diagram a little bit. So parallax for a point is given by the coordinate in one coordinate system subtracted from the coordinates in the other coordinate system. So let's look at the left-hand side. Okay, so this is one coordinate system, and that is another. Everything here is actually depicted. We're using the prime for the right-hand side. So prime. So OBA, OBA. So the point A is actually being captured, are you okay, twice on the photograph as small a, and then A prime, are you okay? All right, and then the point B here is also being captured as B and then B prime. But the center of the coordinate system, the photo coordinate system, let's take note of it, is O, is that okay? So that's the center right there. Now take note of B, the position of B, and then what it was before. It was on the left-hand side of the principal point, which is the center of the photograph. So the center of the photograph is called the principal point. All right. And then we have A being on the right-hand side, but it seemed to have shifted a bit closer to the center of the photograph. So things seem to have moved to the left. I mean, naturally, because we are moving to the right. Are you okay? All right. So I want you to understand that. Now in the coordinate system, photo coordinate system, I think I need to explain to you how it works. Let me go back to my board. The board is being nice to me, so it should keep on doing that. It's not crashing. All right, so this is how the photo coordinate system works. It works like, the coordinate system that we use in surveying, like, no, not surveying, but I think maybe in plotting graphs. Are you okay? So the positive values for X, obviously, this is the fly direction. Is the X-axis. I'll keep saying this. So if anybody gives me the wrong answer, I'll know how to do. All right. I keep saying that this is the X-axis, and then it's 90 degrees to the Y-axis. Okay, so it's 90 degrees here, but I won't draw that. I won't put that there. All right. Now, so positive. This is negative. This is negative. Is that okay? So the coordinate of a point somewhere here will now be positive values. So it's be like maybe 2, 2. Are you okay? Meanwhile, the coordinates here will be, say, 2, -2. Are you with me? And the coordinate here will be -2, -2. So this is how the photo coordinate system works. -2, 2. Are you okay? For any particular point, are you okay? We have to put a sign to it. So what it means is that the center, which is the principal point, defines the principal point defines the center or the origin of the coordinate system, and it is 0, 0. Okay. All right, let's go back. I just wanted you to put that in your mind because we need that. We are about to, superimpose an overlay. Superimpose an overlay is the same thing. It's okay. We are about to overlay the two coordinate systems. So on the right-hand side here, we are doing an overlay. Let me move this aside. All right, so now this line here, okay, if you can see that line, that is the principal line. Okay, principal line. The principal line goes to the principal point, okay, through the perspective center, or if you like, the center of the lens arrangement. obviously. And so from the lens to the focal in the image plane, then we have the focal length. So I want you to remember certain things. So it means that from here to here is actually F, which is the focal length. You need to know the focal length of a lens. Is that okay? Right. It's actually the focal point is where the images or the distance, okay, the point at which all the image, you know, all the light rays are going through the lens. Are you okay? Focusing. That's why we call it the focal length. Focal length. All right, great. So let me undo this. Not looking very nice. There you go. So in the superimposition, look at B. B is on the right hand side. So if I actually draw a long line, it's on the right hand side of the principal line. Are you okay? Okay, A is on the right hand side as well. In fact, A is this one here. Okay, and now take note of the fact that we have superimposed L1 and then L2, okay, over there. Okay, and then we can now have O and O prime, which is actually this point here, at the same point. So the O prime you are seeing here, okay, it's actually referring to this point. It's referring to this point. Okay, so in the superimpositions, I want you to appreciate the fact that we are overlaying two things with a common exposure station, common principal point. Is that okay? And the rest are points that exist that seem to have moved a little bit. Are you okay? Because B refers to the ground point, capital B. See, small b refers to capital B, and then B prime, small b prime, also refers to the same B, but these are just images. Are you okay? So we've taken two pictures of the same object. It's all right, and they are appearing at two different locations. It's all right. So what it means is that they are going to have two different coordinates because they don't remain the same at the same location with respect to the common coordinate system whose center I'm showing up here. Where is it? Okay, so the center is here. Okay, I was looking for my spotlights, which seem to have disappeared from the list. Okay, so now you need to appreciate this. The aircraft has moved from L1, L2, but then we've taken the photographs and we've superimposed it. Is that okay? Now, when we do the superimposition, the difference in where I was and where I am now is the parallax. The difference in where I was and where I am now in the X direction is the parallax of the point. So now parallax of point B then becomes the distance between, get my line, the distance between B and then B prime. And then the parallax for point A is A and then A prime, which is from here to here. Is that okay? So this is the basic explanation of how parallax works. Is all right. So the rest is just playing with the concepts. If you have any question, you can ask. Otherwise, I'll move on. I'm assuming you understand what is on the board perfectly. And I don't think it's that complicated anyway. So that is parallax for you. The whole idea is to now derive formulas. Are you okay? So we're going to come to the parallax equations. Is all right? Which we want to see how they can benefit us. For example, the height. Remember we said parallax has everything to do with the elevation of a point, and that high points have, high large parallaxes compared to low points. Is that okay? So the parallax of point A is higher than the parallax of point B. Okay, parallax of point A, because it's higher, it looks higher. Are you okay? So in that case, if this were a datum, yeah, then obviously we can talk about this height here and that. So this would be HA, capital A. Anytime we use capital letter, remember that we are dealing with ground coordinates. H, E, and then we can do that. Okay, so, right, I'm moving on. I think it's clear to everyone. I'm recording this, so hopefully maybe I can share it with you. All right, so parallax, I think, is very easy to understand. We shouldn't really struggle with it. Parallax measured in flight line axis system. So we need to understand that you can never measure parallax if your flight line is not really kind of coinciding. Are you okay? The actual travel path for the aircraft may change. Is that okay? It may change. But then you need to recognize that it's very important for the photos to be aligned. It's very important for the photos to be aligned. Okay? All right. That is it. It's okay. We need to recognize that the aircraft may not necessarily move in a certain straight line. It's very important. It's basic theory. All right, let's move on. Monoscopic parallax measurement. That means that I'm measuring parallax without considering the two photographs at the same time. So it's like a manual way of calculating parallax. I'll go and then I'll measure, are you okay, the distance between two photographs, and then I'll now subtract the separation between the any 2 points that appear on the two photographs, and then I'll be having the parallax of the point. So as you can see on this diagram, this becomes the parallax D, okay, here, minus DB. So it means we are looking for the parallax of point B, okay, and then D is the separation between the two photographs. Is that okay? So capital D is separation between the two photos. So how do you find that? You just look for the center of the photographs, of course, and then you are good to go. Is that okay? So this is a very simple formula, and I believe you can all use it and appreciate it. Okay. All right. Let's move on. I don't know if we talked about the principle of the floating mark, but the floating mark, have we talked about it? I think we did anyway, or maybe in another class. Yes, the floating mark is actually a way of creating your own like object, virtual object, by actually drawing a mark, okay, on a clear glass, making it something like a cross on it, and then putting it on, an image, and then separate their separation. If they are really aligned, then their separation also creates the same effect that you get when you have two separate photographs. Is that okay? All right, so we have identical marks that are used in the floating. It's very important. Is that okay? Every single one of them is called half mark. Everybody who has been to service school knows what I'm talking about. So why am I even talking about it? Yes, but I think this is like a revision for you. I believe you appreciate it. Okay, so we can move them apart, move them, closer together, and then they seem to be falling or rising. Are you okay? All right, and so the last one down here, we are saying that spacing of half marks since that they are parallax are varied, so floating marks appear to rest exactly on the terrain. Are you okay? So we can just play with it. It's a very nice way to trick ourselves to believe that there's a mark that's actually lying on, are you okay, the surface of interest. All right. So the parallax of the principal points for the left photograph and the right photograph are very interesting. Are you okay? So we've decided to write something about it over here. The parallax of the left ground principal point is the photo base measured on the right photo, and the parallax of the right ground principal point is also photo base B measured on left photograph. So what we are actually saying is that when you take a photograph, you can identify the principal point of the other photograph on Okay, so you can find the principal point of, if there are two overlapping photographs, when I look on one photo, I'll be able to find the principal point of the other one on it. Okay, and if I measure the distance between my current, points, then I'm in a position. Okay, we have 10 minutes, but when it ends, kindly rejoin with the same link. So if I look for this point here, okay, then I can now measure the distance between this and that. I'll be having B. Okay, and I can do the same thing over here. I look for this point here. Okay, when I move forward, obviously this point is going to move backwards. So let's also remember that. So it's going to be somewhere here, not here. Okay, so let's undo and do it well. Right, this point, when I move forward, it should be somewhere there. So now this will be B prime, and we are saying that B and B prime are approximately the same, and they actually represent the alternate parallaxes for the principal point. Please, this one is so simple. What I like about surveying and geomatics and geospatial, technology is that everything we are teaching is so simple that it's difficult to understand. Please, what did I just say? So let me just interact with the class a bit. Let me see if you are following. What did I just say? Anybody? What am I just talking about right now? So I'm going to unmute all of you so that I can hear you. So I only have 3 people listening to me. That's fine. Okay. I'll punish people as and when I want to. All right. So now, please unmute yourselves. And let's find out what I'm talking about. It's important that I just don't keep talking. What did I just talk about here? Unmute yourself. If you can hear me, unmute yourself. Start unmuting yourself, please. Okay, so what did I just explain on the board? I want to hear from you. Every good teacher wants to hear from the class. Get a certain feedback, whether good or bad. What am I talking about? Pilot, unmute yourself. I'm asking for the last time. Nicholas, unmute yourself. Let me hear you. These classes are not like, you're not doing anybody a favor. We are all doing ourselves a favor. Is that okay? So let's cooperate. Juliet is gone. It's okay. I mean, she's always here. Pilot, unmute yourself. It means he's not there. He just joined. Are you okay? People just join the lecture. They don't listen. And then they go away. And I don't think that's really good. You shouldn't be doing that. All right. Worry about it. It's even easier that way. If you don't want to understand it, I don't think so. And I'm cool. I'm good to go. All right. So let's move on. All right. So here we go. That's what we just talked about. We can make use of an instrument, okay, called a parallax bar in the measurement of stereoscopic parallax. Is that okay? All right. As opposed to monoscopic parallax, where we just find the separation between the points, we just use a ruler. We can actually measure, using this bar. It's very interesting. Okay, a few things to note about this parallax bar is the constant K, okay, over here, and then the reading that we take to any 2 conjugate points. So A and B, A and A prime are actually known as conjugate points. Okay, so A and A prime. So similarly, B and B prime are so-called, okay, you can call them also conjugate points, okay. In other words, there are points that can be identified, say the corner of a building that appears in the overlap region. So, and also remember that the overlap region is actually somewhere here, 60%, okay, they are all around here. So immediately we go beyond that, we are going to find it a bit difficult. Are you okay? Can't go beyond that. Are you okay? All right. And then this area is also out of the overlap region. But like I said, it's very important to appreciate the fact that we measure parallax for a point and its conjugate point. That is the point I wanted to make. And so in this example, we have the instrument is actually made up of, it's a very simple, very simple. We can adjust a movable mass, half mark, and then we can have a fixed half mark. Are you okay? So that you don't move this one, the one on the left hand side, but you can actually move the one on the right hand side, and then you can read from, you know, a scale. Are you okay? Some kind of vernier scale or whatever you want to call it. But you can move this, shift it left and right, and then there you go. You can move it here in this direction. You can move it in this direction as well. Okay. All right. Not working very well. Okay, so there we go. Right. Of course, parallel to the flight line, okay, which is actually this line here. This is a flight line. Okay, so that drawing isn't going very well. Okay, but then you appreciate it's an arrow I'm trying to draw to the right, and here to kind of an arrow showing that we can move this. Are you okay? So we move it to the point of interest, okay, and then we are good to go. All right, so a few formulas can be derived. We can actually do a certain derivation. All right, so in here, we can actually say that since parallax is xa minus xa prime, then we can also say that it's equal to the d. Okay, what is d? Let's go back and look at d. Okay, d is the separation. Remember we talked about d minus db. Okay, d is the separation between the photographs. K is the constant, parallax bar. Okay, a constant for the instrument, different from C, the parallax bar constant, which we're about to talk about. Okay, so now D minus K minus the reading. Okay, so the reading is actually shown up here. Okay, so remember we can adjust the movable half mass and then take a reading. Okay, and so moving forward, we can now use that reading in here. All right. Now, so D minus K plus RA, remember that the constant is actually C equal to D minus K. Okay, so we just replace D minus K with C. Okay, so in maths, when you actually write, of course, 2 minus 2, what you are getting is a constant. And then the 2 is a constant, the 3 is so 2 minus 3 is a constant. Okay, 2 is constant, 3 is constant, the answer is a constant. That's what we are doing over here. All right. So let's clear this one. So we can now reduce the formula to the parallax at any point is a constant plus a reading. So that's how the parallax bar works. Are you okay? We simply use this simple relationship. Are you okay? Now it's very important to realize, how do you get C? You get C by simply measuring it monoscopically. We can obtain C because we make C the subject of the relation up here. Okay, so we take R to the other side, then we have P minus R, and then we can put the C back into the equation, and then we are good to go. All right, so now what follows is just a development of the parallax equation. We are not going to, like deriving it and all that, but we need to appreciate the geometry, okay, of some of the things that we are doing. Okay, so a diagram like this is interesting. I always find it very interesting. Look at the datum. The datum is actually, a plane, okay, a reference plane, like I said, this line here. Okay, so this is along the y-axis. Okay, so but the datum really is actually an area. This whole area here is a plane, not an area, a region. So if you actually extended this, let's assume this were the, mean sea level, then obviously you can imagine, okay, So that is the day 2 for you, and a point P actually is actually we can measure the height of a point P, all right, with respect to the day 2. All heights are measured with respect to a day 2, so the H. All right. So the X